I didn't go home. I live here. Yeah. I turned back to this. Yeah, you live in the village. It's not bad. It's just more convenient than that. No, I understand. When I live there, I don't feel bad living there. We can see rooms. Yeah, just one. Or just like not too bad again. Yeah, you are really this one. It's fine.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. I think we're gonna have a little bit of noise outside. I think there's some kind of festival going on, and there's always a festival next door with the seniors. So I apologize for the sound. Okay, but today should be a fairly short day, so I am kind of cutting this Fourier transform section a little bit short, just so that we finish up, before before the midterm. So today we're going to be talking about finishing up our discussion of Fourier transforms. So we'll be talking about something called the Gibbs phenomenon. We'll be talking about the complex form of the Fourier transform, and then some application to something called a power spectrum, which is probably the most common place where you'll see the Fourier transform out in the wild, out in practice. Okay, so some announcements. Remember, the second midterm exam was postponed. So originally it was going to be a week from today, April 17th. But I did push that back to the following Tuesday. So it's now on Tuesday, April 22nd. So next week I'll be posting kind of all of the pre-midterm stuff. So study guide. I actually have a sample exam for you guys to look at for this exam too. So I'll post a sample exam for next week. And we'll start kind of ramping up for that as well. Okay. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So we were looking at Fourier integrals and Fourier transforms. Okay. So Fourier integrals and Fourier transforms, this is kind of an extension of our discussion of Fourier series representations, right? And so the idea with Fourier is that, this gives us kind of an alternate way to represent our time domain functions. Okay. So for the Fourier series representations, that was for specifically periodic functions. And Fourier transforms, we kind of extended that same idea to non-periodic functions. Okay. And so even just, and so actually to draw the comparison, let me go ahead and draw both for you here. Okay. So first we have our Fourier series. So Fourier series representation looks something like this. We have f of t is equal to a0 plus summation from n is equal to 1 to infinity, an cosine of n pi t over L plus bn sine of n pi t over L. Okay. Right, so we basically take our time domain function f of t and we represent it as a summation of sine and cosine terms. Okay. And this works because, sine and cosine are themselves periodic functions. And so when we sum them all up together, we end up with the periodic function as well. Okay. And just like you have been doing on homework 5, we have our formulas for the ANs and BNs. Actually, let's start with A0. So A0, remember, is a 1 over 2L, integral from minus L to L, f of t dt. Okay. We have AN is 1 over L, integral from minus L to L, f of t, cosine of n pi t over L dt. And then we have Bn, same thing, but with sine. So 1 over L, integral from minus L to L, f of t, sine of n pi t over L, dt. Okay. Okay, so that was our Fourier series. Right. So that column there kind of summarizes kind of everything we did, you know, the week before we left for spring break. Okay. Now this week we're going over kind of the integral representation instead. So we're looking at a Fourier integral representation. Okay, so I'm putting them side by side just to kind of illustrate to you that this is kind of the same idea, hence, you know, hence the name Fourier. It's just that, you know, one works for periodic functions, Fourier transform works for non-periodic functions. Okay. So for the Fourier integral, we have f of t, right? Once again, we have our time domain function that we want to represent. And instead of a summation, we have an integral instead. So we have integral from 0 to infinity of a of omega cosine omega t plus b of omega sine of omega t d omega. Okay. So hopefully you see the kind of the similarities between the Fourier series representation and the Fourier integral representation. Okay. And of course, we have our formulas for a of omega and b of omega, which essentially take the place of our coefficients. And so we have a of omega is equal to 1 over pi integral from 0 to infinity, or excuse me, minus infinity to infinity of f of t cosine omega t dt, and then b of omega is 1 over pi integral from minus infinity to infinity f of t sine omega t dt. Okay. Okay. So these are really kind of, you know, two, you know, hopefully you kind of see the similarities with these two. And, you know, I try to use kind of similar symbols here to kind of illustrate. Okay. So, you know, for this week, you know, we're focusing mostly on the Fourier integral side, right? But, you know, this is really just an extension of kind of everything that we've done. Okay. And specifically, these two expressions right here, right? You can think of these as a transformation of our function from the time domain to the frequency domain, right? So because what we put into this, we put a time domain function f of t, okay? And then what we get out of it is some function of frequency, okay? So these things in the box here, you know, these are what's called the Fourier transform. Okay. Which, you know, is similar to what we did before with the Laplace transform, right? So whenever you have a transform, that basically means that you're taking your function, you're performing a change of variables, so that you're putting it in a different form to highlight different kinds of behavior about the function. Okay? So the Fourier transform basically takes transforms a physical domain function to frequency domain. Okay. And you're going to see, you know, once we kind of get to the power spectrum and some of the applications, that this has a lot of really interesting applications for engineering analysis of signals. If you're an electrical engineer, this is something you're probably going to work with on a regular basis. You probably you've probably already done labs with oscilloscopes, things like that. Okay. If you're a mechanical engineer, or civil engineer, it's still important. We use frequency domain in kind of a different context. We mostly use it to talk about vibrations and resonance. So it still has its place, but frequency domain analysis is important for all different kinds of. Okay. Okay. So that's kind of just a summary of kind of how we got to this point. Any questions on this? Okay. All right. So first new thing that I want to talk about today is this interesting phenomenon that you get called the Gibbs phenomenon. Okay. So both the Fourier series representation and the Fourier integral, they give us an alternate way to represent our functions, right? But something interesting actually happens when you do provide this alternate, alternate representation. Okay. So when you represent a function using sine and cosine, something really interesting happens when you start to truncate the representation. Okay. So remember, before spring break, we talked about this idea of truncating our Fourier's expansions, right? Because normally, for a full complete expansion, you have to perform an infinite summation, right? So if I scroll up here a little bit, right? And so if you look at, these two representations here, right? Part of these representations is that, one, for the Fourier series, you have to do a summation over an infinite number of terms, okay? And even for the Fourier integral, right? We have to do our integration up into infinity, which, for either case, for both the Fourier series representation and the Fourier integral, oftentimes is not practiced. And so in order for us to actually, compute these in a practical way, either on pencil and paper or even in a computer, we have to truncate these by setting these equal to some finite number. Okay. So we've done a little bit of plotting, right? So remember, the example we did right before spring break, right? We saw what happens when we truncated our series. We get a function that kind of looks like our original function, but had some waviness because of the sine and cosine, right? And so the Gibbs phenomenon kind of describes what that is. Okay. Okay. So in words, the Gibbs phenomenon is basically describes what can be best described as kind of like an overshoot phenomenon when you do truncate these representations. Okay. And so the Gibbs phenomenon, describes this tendency for Fourier representations to overshoot the original function specifically in areas of discontinuity. Okay. So if your original function has any kind of discontinuities or has any kinds of sharp changes in its value, when you represent that using Fourier, you're going to get some overshoot type behavior. Okay. I think the easiest way to draw this is or the easiest way to illustrate this is with the drawing. So let me go ahead and show you what that means. Okay, so let's draw our coordinate axes here. Okay. And let's draw kind of a basic square width, right? And so so this is the example we actually ended with on Tuesday. Okay. And so if we have our original function, looks like this. We have basically a square pulse, a square pulse or a rectangular pulse that we are representing with Fourier. Okay, so this could be a periodic function. You can adjust the parameters and such to be periodic. So you can use a Fourier representation, Fourier series. But you know, let's just look at one wave here. So this is kind of exactly the example that we did. Okay. Okay, so let's see what happens when we try to represent this function using a Fourier integral. So in this kind of purpley color here, I'm going to draw the Fourier integral representation using a cutoff frequency of 8. Okay. 8's a very arbitrary number. But you know, what I mean by that is that, you know, when you go to your Fourier integral representation, right, the upper bound of this integral is going to be 8. Okay. 8 just happens to work out pretty well for this this example. Okay, so when you actually go and plot this, you know, it actually looks like the following. So remember, you know, one of the benefits of using a Fourier integral representation or a Fourier series representation is that if you do have discontinuities, the Fourier is actually going to smooth out those discontinuities. So you'll get a continuous function that looks like the original function here. Okay. Okay, so if you plot it, you know, it kind of looks something like this. So we have something that goes up, goes down, goes up here, and something like this. Okay. So that's what that would look like for a relatively low frequency representation or a highly truncated representation of our original function. Okay. Okay, so let's kind of describe what's going on in this representation. Okay. Okay. So our rectangular pulse here has 2 discontinuities, and so it has a discontinuity on the left-hand side. So here. Okay. And it has a discontinuity on the right-hand side. Basically, whenever the pulse either goes up or goes down, you know, that's kind of an abrupt change in value of the function. So we call that a discontinuity. Okay. Now let's see what the purple function is doing in the neighborhood of those discontinuities. Okay. Okay. So first of all, you know, first thing that you see is that, you know, this purple function is kind of bridging over that discontinuity. So we no longer have kind of a vertical line. So, you know, we have you know, our function is 1-to-1 and it's smooth. Okay. But if you look at these, you know, I like to call them, you know, bunny ears. Right? In order to, you know, try to fit that function and fit that discontinuity as best as it can, you know, we have this kind of overshoot where the function kind of, you know, goes down a little bit and then goes up, but then it goes too far up and it overshoots and then before coming back in. Okay. So these, you know, these overshoots here, these are what's called the Gibbs phenomenon. And that's something that's always going to be present, whenever you have a Fourier, representation. Okay. All right, and so what's interesting about the Gibbs phenomenon is that even if you increase the cutoff frequency, even if you truncate at a later frequency, the Gibbs phenomenon is still present. In fact, it's one of those very, very stubborn things that's very hard to get rid of. So in theory, if you were to do an infinite summation or an infinite integral here, that Gibbs phenomenon would go away. But scientists have kind of shown that even for very high cutoff frequencies, very high truncation terms, the Gibbs phenomenon persists. So it's very, very stubborn and something that you kind of have to live with if you are doing a Fourier representation of a discontinuous function. So after this, I'll draw a couple more examples for you just so you can kind of see. So, if we set the cutoff frequency to 16, 32, you'll see that Gibbs phenomenon is still going to be there. Just because it is very, very stubborn. All right, any questions on this so far? Okay, all right, so let me draw a couple more for you just so you can kind of see. And I want you to kind of take note of some of the other properties or what other things occur when we truncate at a higher frequency or increase the cutoff frequency. Okay. So let's draw our coordinate axes again. Let's draw our square pulse. Okay. I think I made this wider than the one up there. That's okay. Okay. So let's say for this one, we set our truncation frequency to 16. So we're including additional frequencies into our Fourier integral. Okay. So what you're going to see is that, when we increase the truncation frequency, we increase that cutoff, we're going to simulate this or model this function closer, but that Gibbs phenomenon is still going to persist. It's still going to be kind of very stubborn. Okay. 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 So for a cutoff frequency of 16, in blue here, you can see that our function is represented a little bit closer. So kind of those oscillations get a little bit tighter around our function. Okay. But this Gibbs phenomenon still persists. Right. So overall, you are getting more accurate. You're getting better at representing the function. There's less discrepancies, but the Gibbs phenomenon just will not kind of go away. Okay. The proof of this is actually very fascinating. So you can actually mathematically prove that, as long as your cutoff frequency or your truncation is finite, so it's a non-infinite, something less than infinity, that Gibbs phenomenon is always going to be present. It's only when you set the cutoff frequency to infinity, that's when the Gibbs phenomenon kind of truly kind of goes away. So it's a fascinating proof, one that we don't have time for in this class. But one of the coolest ones because it's something that I think visually you kind of really see it a lot. And it's just fascinating how stubborn it is, when you unless you set that upper bound to. Okay. Okay. And then just to kind of illustrate one more time, let me kind of draw one more representation for you. And I'll do it on the same graph just so you can kind of see. So let's see what happens when we increase the truncation frequency to 32. Now these numbers are fairly arbitrary, 8, 16, 32. These are just kind of the nice round even numbers. But the idea is that, as you go from 8 to 16 to 32, you're increasing the frequency. Okay, there's nothing magical about 8, 16, and 32. Those are just the numbers that happen to work well for this. Okay, so if you increase the truncation frequency to 32, you can see the oscillations will get even more fine. Okay, they'll even get more tight. So you can see here that the oscillations get more fine here. But we still have that kind of Gibbs phenomenon. I might have been able to emphasize it a bit more, but you know, we still have the Gibbs phenomenon even in this case. Okay. All right, kind of in a nutshell, you know, basically the proof just says that, you know, when you have sine and cosine functions, you know, they just love to oscillate. And so whenever you're forcing them to make a kind of a big jump like this in the neighborhood of a discontinuity, there's always going to be some overshoot, unless you set it to be. All right, any questions on this? Okay, cool. All right, so let's go ahead and move on to the next topic, which is the complex form of the Fourier transform. Okay. So last time on Tuesday, you know, we went over the Fourier transform, and we say that there's kind of two, you can say that there's kind of two versions of the Fourier transform. There's the A of omega function and the B of omega function. And so those two functions have their own names, and so those are known as the cosine Fourier transform and the sine Fourier transform. Okay. All right, so I'll write them down here just so you can see them again. So A of omega is equal to integral from minus infinity to infinity, f of t cosine omega t dt. Okay, so we call this the cosine Fourier transform because, you know, we're multiplying our function by cosine and taking the integral of that. Okay, and then the sine transform b of omega is equal to integral from minus infinity to infinity, f of t sine omega t dt. Okay, so, you know, we always start with these ones when you're first introducing Fourier, just that these are the forms of the Fourier transform that kind of most closely resemble the Fourier series. But, you know, having to compute two transforms for a given function can be kind of annoying, right? Sometimes this is useful because, you know, if our function is even or odd, then, you know, you can make that simplification here. But a lot of times when you have non-periodic functions, you know, you don't really have the luxury of an even or odd functions. Okay. So the idea of the complex form of the Fourier transform is to kind of have just one formula, one way to compute the Fourier transform without having to do two separate integrals. Okay. And so, you know, we want to answer the question, you know, is there a way to compute just one transform that kind of captures both behaviors at the same time? Okay. So of course, you know, that's answer to that is yes, right? And to do that, we're going to make use of you know, a formula that, you know, you may have seen before. Actually, you know, we've already used it in this class, which is Euler's formula. So it turns out you can relate sine and cosine together with a complex exponential, because we have this relationship from complex math, right? So we have e to the I times x is equal to cosine of x plus I sine of x, okay? Remember, we went over this when we were talking about our solutions to second order ordinary differential equations with complex conjugate roots, okay? And so knowing that this relationship exists, the question is, can we use this relationship to kind of combine these two sine and cosine transforms into just one Fourier transform? Because, that's what we did for Laplace transform, right? So Laplace transform, we had just one integral to transform our function. Let's do the same thing with Fourier, okay? And so, once again, kind of skipping the details of the derivation, although, it's not really that big a deal here, just because you're just basically just taking these two and adding them together, okay? The only thing that really comes out of the derivation is that there is there is an additional scaling factor out in front, okay? Okay, so this form of the Fourier transform, this is the one that's often, cited in the literature, right? And so when people talk about the Fourier transform, they usually mean the complex version of that transform, okay? So the complex version of the Fourier transform, we usually give it the symbol f hat of omega is equal to 1 over square root of 2 pi, right? That's kind of that factor that comes out in front, multiplied by integral minus infinity to infinity of f of t e to the minus I omega t dt. So this formula right here, this is the complex form of the Fourier transform. Okay. Okay, so for most situations, if a problem asks you to compute the Fourier transform or something, they're usually referring to this, right? And the reason we have this one again, is mostly just due to the presence of Euler's formula, which combines the sine and cosine terms, right? So we're still making a transformation to the frequency domain, except instead of computing the cosine components and the sine components separately, we're doing them all together in one, utilizing this kind of complex exponential. Okay, any questions on this before we do an example real quick? Okay, all right, so let's do an example just so you can see how it all kind of comes together. Okay, so for this example, we want to find the complex Fourier transform of a basic decaying exponential function. Okay, so our function here is going to be piecewise. There's going to be a discontinuity. So it's going to be 0 when t is less than or equal to 0. Okay. And then when t is greater than 0, our f of t is going to be e to the minus alpha t. Okay, so this is a perfect candidate for the Fourier transform because we have, first of all, we have a non-periodic function. And so this is not something that we can do a Fourier series expansion for because there's no way we can compute a period from this. Okay. And so if we wanted to transform this function into the frequency domain, we have to use a Fourier transform. And in fact, the best option for this is going to be the result that we have right above. Okay. Okay, so let's go ahead and plug in. So we have f hat of omega is equal to 1 over square root 2 pi, integral from minus infinity to infinity, f of t, e to the minus I omega t dt. Okay. So let's go ahead and plug in our function, and let's also take into account the sections of the function where it's equal to 0. Okay. So since this function is 0 for all values of t less than 0, that means we can start this integral, instead of going from minus infinity to infinity, we can just integrate from 0 to infinity instead. Okay, so if we plug in for that, we still have a 1 over square root 2 pi out in front, and then we have integral 0 to infinity. Okay. F of t here is e to the minus alpha t. And we're going to multiply that by e to the minus I omega t. And we're integrating with respect to t. Okay. So this integral here is fairly simple, so we can just kind of combine these two exponents together. Okay. So since we have e to the something multiplied by e to the something, we can just combine them into one e, just add their exponents together. Okay. So this is equal to 1 over square root 2 pi, integral from 0 to infinity, e to the minus alpha plus I omega t dt. So now we just have integral of an exponential function, which is very straightforward. So we're going to divide by, the coefficient in front of t. So that's going to give us minus 1 divided by square root 2 pi multiplied by alpha plus I omega e to the minus alpha plus I omega t, evaluated from t is equal to 0 to t is equal to infinity. Okay. So let's go ahead and plug in for t, plug in our integration bound. So first, we have t is equal to infinity. So that's equal to, let's not forget our constant out in front. So we have minus 1 over square root of 2 pi. That's alpha plus I omega. We have e to the minus alpha plus I omega t times, t is infinity. So you have e to the minus infinity minus e to the 0. E to the minus infinity, we know, is going to asymptote to 0. So that is a term that we can cancel out. Okay. And then e to the 0 is just evaluated at 1. Okay. And so we plug all this in, and what we get is our final answer. F hat of omega is equal to 1 divided by square root of 2 pi multiplied by alpha plus I omega. And that's it. Multiplied by 1, minus 1. So minus 1 cancel out, and so our result is positive. All right, any questions on this example here? Okay, good. All right, so last thing I wanted to talk about today is this idea of a power spectrum. So this is probably the most common application of Fourier transforms, in I would say kind of modern engineering work or modern engineering analysis. Okay. So let's talk about power spectrums. Okay. All right, so the idea with the power spectrum kind of goes back to our interpretation of our Fourier series coefficients. In fact, this interpretation kind of goes to both Fourier series and Fourier transforms, but I think it's easiest to kind of introduce the idea with the Fourier series coefficients. Okay. So in a Fourier series representation, okay, the values of our coefficients, actually do have some significant value to our functional representation. Okay. In particular, I'm going to look at the magnitudes of the different coefficients. Okay. And so based on the magnitudes of the Fourier series coefficients, you can basically make a statement in terms of, how much power, how much energy is in that frequency in your original signal. Okay. So this is actually a question on the last homework. So this is problem 3, I believe, on the last homework. So, probably from there, it didn't make too much sense, but, this kind of gives you the context of, why I had you do that problem. Okay. Okay. So for example, let's write out a Fourier series representation, and I'm just going to kind of make up some of the numbers of the coefficients, right? The exact values here aren't too important. What's more important is kind of the relative values of those coefficients relative to each other. Okay. Okay. So let's say we have f of t is equal to. Let's just do the first 3 terms, and let's say that we have an odd function. So we have b1 sine of pi t over L plus b2 sine of 2 pi t over L plus b3 sine of 3 pi t divided by L. Okay. So we have 3 terms in our representation. Okay. All right. So let's say that, our value for B1 here, we'll say has a value of 5. Okay. So this 5 sine pi t over L plus, we'll say our value for B2 is, 8 sine 2 pi t divided by L. And our value for B3 here, we'll say it goes down to 2. Okay, so those are our coefficients. We have 5, 8, and then 2. Okay, so what can we glean about this function based on the values of those coefficients, right? So first one we can look at is, which of these coefficients is the highest? That is the 8, right? Okay, so the fact that 8 is the highest coefficient here, in terms of power, that this tells us that most of the energy, or the majority of the energy in the function, is concentrated in this term right here. Okay. Okay. And what's unique about this frequency, or what's unique about this term, is that it has a set frequency, right? So the frequency of this term we can tell just based on what's inside the sine term, right? And so this particular term has a frequency of 2 pi over L. All right, I had a double take at my phone because my wife texted me. She said she got poisoned, so I got worried. But then she's playing Pokemon. She's not. She didn't eat anything weird. Just her Pokemon got poisoned. Little bit of a panic attack, right? Okay, anyway, so power spectrum. So based on the value of these coefficients, we can tell how the energy is scattered within these different frequencies, right? If we go back to kind of our original discussion when we first introduced Fourier, remember we first introduced Fourier under the context of sound, right? Right, and we said that sound primarily has two different components, and so there is a volume and pitch, right? Where volume, remember, is we characterize that as the amplitude of our periodic function of our pressure waves, and pitch is the frequency, right? Turns out that these two things are paired, right? And so if you look at kind of the frequency content or the pitch content of any kind of, I would say, real life sound, you'll see that it consists of many different frequencies. So, you guys listening to the, my voice right now, my voice is not coming out at a constant frequency. My frequency and the volume is constantly going up and down. And the combination of all these things together kind of makes what we perceive as sound. Okay. But with that said, there are certain frequencies within a particular sound that are more prominent than others, right? And so, my voice fairly low. And so, for the lower frequency sounds, if you did kind of a power spectrum of my voice, you'll see that, those frequencies will have a higher volume compared to others. Okay. So that's one of the main benefits that we get from a Fourier transformation or Fourier kind of series, decomposition, is that, we can basically decompose any kind of complex signal and say, where most of the energy is in how most of the energy is scattered in terms of the different frequencies. Okay. Okay. And so a power spectrum, all that really refers to is just, listing out all the different values of the coefficients kind of one after another. So you can correlate, each coefficient with each frequency. Okay. And so if you were to plot it, and so, probably the most common way to view the power spectrum is something like this, right? So on the horizontal axis, we have frequency. Okay. And on the vertical axis, we have magnitude or power. That's probably the better way to describe it. For a Fourier series representation, you're going to see this power spectrum represented as a histogram. Okay. So you're going to see, some bars like this, maybe go higher. Okay. Because remember, with the Fourier series, you have a discrete number of these coefficients, right? And they're all separated by, a fixed amount of frequency. Okay. But from the power spectrum, you can see that, in this particular graph, maybe these frequencies or these are the most dominant frequencies because they have the highest magnitude compared to all the others. Okay. frequencies, there's two of them. So the only difference between a Fourier series representation and a Fourier integral or Fourier transform is that for a Fourier transform, you get a continuous function in frequency, okay? And so if you were to plot it out, you know, the Fourier transform might look something like this. So they both kind of show the same thing. It's just that, you know, one is discrete in terms of discrete coefficients. The other one is a continuous function of frequency. Okay. And specifically, you know, when you do plot the power spectra, generally you plot the absolute value of the coefficients, because sometimes the coefficient can be negative, as you guys have seen in the homeworks. Or another common way to plot the power spectra is to take the square, right? So you have an squared, bn squared, or maybe you have f hat of omega quantity squared, okay? Because when you square it, you're guaranteed to get a positive. Okay. So if you go back to problem 3 on homework 5, you know, this is essentially what I showed you, was that, you know, I showed you guys the power spectra for that given application, okay? Now, this has a lot of different applications. So, you know, obviously there's applications to sound mixing or sound, you know, recording sounds, digitizing sound, modifying sounds, things like that, okay? Another important application that was described in the homework was identifying the resonant frequency of a structure. Right? Remember when we were talking about second order differential equations, we talked about this idea of resonance and how it's dangerous, and generally you want to avoid resonance when you're designing, you know, designing a part. The challenge is that, you know, when you have a very complex structure with complex geometries, complex loading, complex conditions, it can be very difficult to identify what the resonant frequency is. And so one thing, or one way that engineers and scientists do identify this frequency is to do a impulse test. Okay. Right. So the way impulse testing works is that you know, you take your structure and then you provide some kind of impulsive loading. So remember impulse function we talked about before. You know, maybe we provide a force that's very short, very brief, and very, you know, strong. Okay. So after we provide kind of an impulse forcing to the structure, what we can do from there is observe its vibration, observe its response. Okay. Okay. Because usually, you know, when you strike a structure, right? So let's say that we have, you know, some structure here, right? My structure is going to be a cube because I can't draw. Okay. Right. So let's say we take this cube and we just kick it. Right? So we just provide some impulsive forcing, right? And so what happens is that this cube is going to, you know, vibrate, right? I tried to draw vibration animation things, but it didn't work out. But imagine that the cube is vibrating, right? Any structure that you strike very quickly, it's going to have some kind of vibration, okay? And if you have some kind of sensor on the outside of the structure, then you can observe its vibration, right? And so typically the vibration is given in terms of a graph like this, where the horizontal axis is time, vertical axis is displacement. Okay. The thing about structural vibrations that they often occur very, very quickly. So you have very kind of quick oscillations. And so you maybe get a signal that maybe looks kind of something like this. Okay. All right, it's going to be a messy signal, no matter kind of how you kind of slice it. Okay. All right, so from this signal by itself, it's very difficult to determine, what the resonant frequency is, just because all the vibrations are really kind of crazy. And really, you have kind of multiple frequency vibrations here kind of occurring at the same time. And so if you want to identify the resonant frequency, what you can do is you can take the signal, right? This very, very messy signal, and then apply a Fourier transform or a Fourier series representation. Okay. And so by doing a Fourier transform, we basically are transforming this time domain signal into a frequency domain signal. And then from there, we can identify which frequencies have the highest amount of energy or power in this original signal. Okay, so if we perform our Fourier transform, right? So this is going to give us some function f hat of omega, right? So let's say we perform the complex version of the Fourier transform. Okay. So this is the same signal. So this is kind of the same messy time domain signal. But after we perform the Fourier transform, it might look something like this. It might still be a little bit messy. Okay? But what you should see is that there should be some patterns that emerge from the data. Okay. So the Fourier transform or the power spectra should have a few distinct peaks that tell you what the resonant frequency of that structure is. So that's how resonant frequencies of a structure are traditionally kind of obtained, at least from physical testing. Now you can do a lot of it in simulations, but before those became a big thing, this is kind of how it was done. So you would get a signal, do some impulse testing, and then to perform the Fourier transform and obtain the frequencies this way. Okay. Any questions on this so far? Okay, so one last application before we head out. Another common application for Fourier is to do what's called a low pass filter. Okay. So a low pass filter is kind of a very basic way to take some kind of messy signal and smooth it out. Okay. So your phones, any kind of device that emits any kind of signal is going to have some kind of low pass filter. Probably it's going to be more sophisticated than what we're going to talk about here, but this is essential whenever you're trying to pass a signal through a noisy kind of environment. Okay. So any electric signal that you kind of observe out in the physical world often comes with some degree of noise. The noise can really just be any kind of interference that happens within the signal itself. Okay. All right. So for instance, right, So let's say that we have a signal that kind of looks like this. So we have kind of very kind of messy, kind of noisy signal that's going on. Okay. All right. So underneath this function, there is a signal that we can actually use, that maybe you're using to connect through Wi-Fi or to get data or something like that, right? But really, right now, it's kind of hard to kind of see that signal underneath all of this noise, right? So there's a huge amount of research. There's a huge amount of skills that go into what's called signal processing. Okay, so on a very basic level, one interesting thing about noise is that noise is always what we call very high frequency. Okay? And so what that basically just means that noise is always going to cause, very, very, very rapid oscillation that occur on a very, very short time scale. Okay. So if we wanted to smooth the signal, if we want to kind of filter out that noise, we can take advantage of the Fourier transform. Okay. So if we apply a Fourier transform to the signal, it's probably going to look something like this. Okay, so we apply a Fourier transform, we plot it, and so we basically get our power spectra. So probably what you're going to see is that there's probably going to be a huge concentration of energy kind of at the lower frequencies. Okay. So that huge concentration of frequencies or that huge concentration of power is likely the true signal, the one that we want to actually kind of measure. Okay. And then at the higher frequencies, there may be some kind of noise that's out here. All right, so in this case, we want to keep the true signal, but we want to filter out all the noise. Okay. So thankfully, we have a way to do this, right? So, what if we basically reconstruct our signal, but we truncate it at a frequency that's, above our true signal frequencies, but below the noise. Okay. So we basically take advantage of the fact that we can take any Fourier representation, Fourier series or Fourier transform, and truncate it at an arbitrary frequency to basically only keep all of the frequency components to the left of this. Okay. All right. So if we cut it off here, basically we're going to be effectively filtering out that noise. That noise is no longer going to be part of the signal. Okay. And then if we reconstruct this function, using only those lower frequencies, we're going to get a much cleaner signal. I'm trying to make it so that you can see kind of everything kind of on one page here. Okay, so you reconstruct the signal. Maybe it looks kind of something like this, right? So you can see that our reconstructed signal has none of those high frequency oscillations because we filtered them out using our low pass filter. Okay. So if you do any kind of work, in signal processing, signal measurements, things like that, obviously, this has applications in electrical engineering, but even in mechanical and civil engineering too, you're going to be dealing with kind of physical instruments to measure things, either in your experiments or maybe out in the real world. And all of those signals are going to require filtering of some kind. It's really impossible, if you're measuring something outside, especially if you're measuring it in kind of a busy environment, like, in the middle of the street or something like that. it's really impossible to get a signal that's devoid of any kind of noise. So, you need to know, how to filter the signal and, or at least how the signal filters work. So you can make, use of the data that you. Okay. All right, any questions on this? Okay, all right, so that's all I got for today. So we'll call it a bit early. When we come back next week, we'll start the final unit. So I will say this right here is the cutoff. So nothing beyond this point is going to be on midterm 2. So this is midterm 2 cutoff. Okay. So on Tuesday, we're going to be starting our unit on probability and statistics. So probability and statistics stuff, that stuff will be on the final, but it won't be on midterm 2. Okay, remember midterm 2 is going to be on Tuesday, April 22nd. All right, so thank you guys for coming today. Hope you guys have a good weekend, and I will see you guys next week.
Is that radios?
Okay.
Is that how radios work?
Kind of. So radios, the way they work is that they have a receiver that's picking up a particular frequency. And so the way a receiver works, it's actually a low pass and high pass filter. They're actually filtering everything below the frequency that we're looking for and everything above the frequency.
Oh, so it's
Exactly. So when you tune it, you kind of slide that frequency.
I see.
And so in the air, right now, all radio stations are sending out their signals.
Yes.
It's just that you set your receiver to only filter out the ones.
Well, I think I saw,
That's cool.
Yes. Mhm.
that. Yeah.
Hello?
Hey, David, sure. What's up?
Yeah, I just wanted to ask
Are
you.
you on voice? Let me see if I can raise the volume here. Let me see, make sure the.
Hello, can you hear me?
sound is on the computer. All right, go forward.
Hello? Can you hear me?
Thursday.
Oh, I hear, I see your mic's going, but I don't hear anything coming out. Do you want to type your question in the chat? Sorry about that. I think this podium just doesn't have sound.
My God.
Oh, of course, yeah. Yeah, let's just send me an email to remind me. Yeah, so for all the formula people, yeah, I have some formula guys in my 407 class too. Yeah, that's no problem at all. We'll probably set up a time. Are you available the Friday before finals week? That might work out the best. Or we can coordinate the schedule. Yeah. So I have Brighton and Bill coming to take the exam on their key transfer exam on Friday before finals week. Probably I'll schedule you for that day too to take a 3-way exam. Yeah. All right, sound good? Okay, cool. All right, thanks, David. Any questions?
Yeah, just question like, what, type elective you're gonna be teaching for next semester?
Okay. So normally in the fall, I teach the finite elements 410.
410.
But I'm actually not going to be here in the fall.
Oh.
It's not because, well, I don't think I'm getting fired, although I may still. But if I'm still employed here, my wife's actually pregnant with our first kid, so I'm going to be taking maternity leave in the fall.
Anyway.
So I'll still be doing advising in the fall, but I won't be teaching.
Yeah, because it's like a lot of us were like, oh, we just take it all together.
Yeah, so I did see that so my other elective in the fall is optimization 454.
454.
So I did see that they did take that one down because I don't think they'll find someone to teach that class. But 410 is still there, so I think they may have found someone else to teach that.
Okay, got it.
Yeah.
Thank you.
And then I have a question,
Sure.
it's kind of unrelated to this, but I saw you sent an email, I think, are you a part of the Tau Beta Pi?
Yep. Mhm.
Okay, because I got an email and I was kind of wondering what it was.
Yeah, so it's a national honor society, and so you kind of join it, and then you're kind of a member for life.
So,
And so-
like, what do you, is there meetings, like, what do you do?
It's well,
Is it like a club kind of?
It's
or
not really a club, it's more of a professional society, so people usually join it to gain access to kind of networking for other members that have, graduated a long time ago.
Okay,
So we have, we have like a conference usually every semester where you get to meet some of the members. We have alumni coming in. There's scholarship opportunities through Talbot applied to. So it's something that, people usually put on the resume too. I don't know how much weight it carries nowadays
okay.
because it's,
Because I was just curious, because it said like society, but I just wasn't sure if it was like something you have to go weekly for.
No. It's honestly, when I joined it back when I was in college, I joined it. And then I wasn't really active at all.
Okay,
And then I came to work here and then they needed an advisor, like, oh, we found your name kind of in the
okay,
database.
because I
So,
saw you
yeah.
sent it from your email,
Yeah,
so
yeah.
I was like, okay, he has to know something about.
Yeah.
Okay.
So I mean, so it's completely student driven though. So I mean,
Okay.
I mostly am pretty hands off. So the members here, I think, last semester they did kind of an elevator pitch, kind of workshop. So to
Okay.
kind of, how to advertise yourself to employers, things like that. So I think they focus more on kind of that
The
aspect of
professional
the
side.
professional side. And I know they're working on doing events to kind of bring in alumni and things like that.
Okay,
But yeah, I think if you have questions, definitely email Alvaro. So Alvaro is our
Okay.
president and he's very happy to answer.
all right, thank you.
Yeah,
Have a good weekend.
you too.